very much for the invitation to speak at this conference on wall crossing. So when I got the invitation, I decided that I would try to give a talk about wall crossing phenomena in pretty much the only case where I think I really understand it at least reasonably well, which is this case of log Calabi-Yau surfaces. So, and I should say, this is, so what I'm talking about to present here is my understanding of this. It draws heavily on preceding work in this area, particularly the work of Gross-Hacking-Kiel, who wrote a very nice opus on mirror symmetry for log Calabi-Yau surfaces, and I'm really going to draw a lot on many of the phenomena that they discovered. Okay. All right, so the outline, so I'll talk a little bit about log Calabi-Yau surfaces. I'll talk about what I want to, the problem I want to ask, or the question I want to ask, which is how can we construct the mirror flare theoretically? And I'll try to explain a little bit about how that construction can be related to counting disks and then actually counting closed curves a la Gross-Hacking-Kiel. And then at the end I'll explain some consequences for other symplectic geometry invariants. Okay, so here's the basic definitions for me for this talk right now. So I'll define a log Calabi-Yau surface. Well, I'll sort of implicitly include these adjectives exact and with maximal boundary. So that's a pair y comma d. Y will be a smooth projective surface, and d will be an anti-canonical divisor. Okay, that would be a log Calabi-Yau surface. I also want it to be nodal, so it's like reduced and nodal. That corresponds to the scientific maximal boundary, which I think is introduced by Gross-Hacking-Kiel. And then I also want it to support an ample divisor. So that means the point of that is that I can take a symplectic form on this space, makes the complement of the divisor an exact symplectic manifold. All right. So, people file in here. So, yeah, so this is my definition of a log Calabi-Yau surface. So an example of a log Calabi-Yau surface, I mean, there's many examples. I think the classical one would be to take y, a cubic surface, and of course, the cubic surface has 27 lines, and they come in various, you can find lines in various configurations. So one configuration you can find is a triangle, so the 3 lines, each intersecting the other 2 at a single point. Okay, so this, and so I'm mostly interested in the mirror symmetry of, I should say maybe the context, I'm mostly interested in mirror symmetry for U, the complement of the anti-canonical divisor. Okay, so how are we going to get a grip on this? Okay, so one very nice thing. So I should say here, yeah, so I should say we're going to focus mostly on the dimension 2 case because there are a number of simplifications in this case that make it a lot easier to understand because of the low dimensionality. The first one is just the topology of the divisor. So you see quickly from the anti-canonical condition that the divisor has to be a curve of arithmetic genus 1, and I'm assuming that it's nodal, so in fact, it's just going to be a cycle of P1s. All right, so that's the first simplification, is that the topology of the divisor is very simple. The next thing you can do with this is you can find a torus vibration on this space, so that's quite useful, of course, for mirror symmetry. So in fact, the only part of the torus vibration that I'm really going to need or care about is the part that's near the boundary. So in fact, what you can do is you can arrange that the symplectic structure on this y comma d is locally toric near the boundary. That means that near each boundary divisor you have a moment map. Okay, so this is what I'm intending to show here. This M is a local moment map. That's the neighborhood of that divisor component to some kind of polyhedron or some kind of open set in a polyhedron in the plane. And of course, when you have this situation, you can get tori, Lagrangian tori, by taking the fibers of these local moment maps. All right. And right, so one of the things that we see here that's a simplification in this case is that there are no singular fibers near the divisor. So because of the low dimensionality, the singular fibers are actually isolated. If you try to extend this, you could, of course, try to extend this torus vibration into the entire manifold, but then you would have some singular fibers. Yes?
So, I mean, is the fact that it's locally toric just the fact that it's got normal, just good
Pretty much, yeah. Well, and no, not just because it has normal crossings. I mean, that would give you that it's locally torqued near the crossings. But, I mean, the fact that it's actually a cycle lets you extend that local torque structure along each divisor. That's right. I'm going to focus on these particular tori. But of course, there's something we can do for any collection of tori. Whenever you have a torus vibration, okay, which is try to construct the mirror FLIR theoretically. So, all right, so I'm following here work of Fukaya, subsequently worked out in perhaps more explicitly by Zhuzhen Tu, and actually the main reference I'm following here is this work of Abuzai, Daru, and Katsarkov for the construction of the mirror. So in this dimension, we can calculate the dimension of the space of this with boundary on LB. Oh, I should say that in the complement of the divisor, each of these tori has Maslov class 0. All right, so you can calculate the virtual dimension of the space of this, which is Maslov index plus n complex dimension minus 3. And okay, in dimension 2, Maslov index 0, you get dimension minus 1. So that means that for generic J, these tori bound no disks. And that means that their FLIR theory is undeformed. All right. So then, when you have the situation, you can look at objects of the Fukaya category supported on this particular torus. And so the objects I want to consider are the ones that correspond to local systems on this torus. Right? And those are classified by the first cohomology of the torus with coefficients in this thing called U lambda. So I'm working over the Novikov ring here, so this lambda here is the Novikov field. Okay, so it's formal series Ci t to the Ri, where the exponents are real and they go to infinity, and the coefficients are complex. And inside there, we have the set of what are called unitary elements, which just means that they're series where all the exponents are positive or non-negative, and the coefficient of the t to the 0 term is non-zero. Okay, so these are unitary local systems. Okay, so the restrictions, you could also consider, just lambda star local systems, just local systems with coefficients and invertible elements of the Novikov ring. But for the analysis of the reconstruction problem, it's important to restrict to this set, okay, because of the issues of convergence. Right, so basically the point is each torus, you get this, each Lagrangian torus, you get this collection of local systems. All right. Now, they're not all distinct. They're not all sort of disjoint objects in the Fukaya category. They're actually related to each other. Okay, so this has to do with, this is Fukai's reconstruction process. So the idea is that if we move this torus, we change it in the family, we want to glue together these sets of, these spaces of objects, of local systems. Okay, so how is that done? Well, in fact, it's a little bit, because of this sort of convergence issues, it's a little bit delicate to do this. So Kai introduced the process for doing this. So instead, so what we do is, so of course, I guess I should say that it's important now to keep track of the almost complex structure all the time. Okay. So what happens here? So, right, because the FLIR theory of an object, this is based on sort of the invariance properties of FLIR theory. And of course, it's the dependence on the almost complex structure comes into play. So we scale it. So here's what you do. Basically, you want to deform this torus, and you have to, perhaps deform the complex structure at the same time. You want to break this path up into two types of paths. Okay, so one thing you want to do. So the problem is that as you move the torus, it's non-Hamiltonian motion, so there's no real reason why it should be invariant. So what you can do there is you deform the Lagrangian in a non-Hamiltonian way, but you also deform the almost complex structure so that there's no, so that your spaces of disks don't change. Basically, that just has the effect of sort of acting on this space of objects by rescaling the coefficients. Now, okay, well, that's not good enough because kind of as you move this torus, you have to move the almost complex structure, but at some point you can't move it anymore. You're going to lose tameness. So at those points, what you do is you introduce another operation, which is another type of family, which I'm calling here pseudoisotopy, which means that you take a Hamiltonian deformation of your Lagrangian, but you allow the JT to vary in a less controlled way. And in this family, some Maslov index 0 disks may appear. And I'm actually counting these Maslov index 0 disks in this family, LT, JT. And in the parametrize problem, the dimension goes up by 1, so now in dimension 2, they will have virtual dimension 0. So you're actually going to get, at sort of isolated values of the parameter t, you're going to get Maslow index 0 disks. Okay, and then the invariance theory for Floer cohomology tells you that these isotopes give you some kind of map, some kind of sort of rational map between the spaces of objects supported on the tori at the beginning and end of the family. And that rational map is a wall crossing transformation. Okay, so this is a way, Floer theoretically, to realize the wall crossing phenomenon for these spaces of objects.
What's the other kind of wall?
So I will say that in a couple slides. So these are called, I'm calling these things walls of the first kind. All right, walls of the first kind. Okay, to be distinguished from walls of the second kind. All right. Let's see. Okay. All right. So maybe here's a picture. Okay. So the idea is you're moving this torus, and then at some point, so this boundary here is supposed to be the boundary divisor of the surface. This U, this is kind of the interior. I'm visualizing. Here's a path of tori, and at some point, as you move this torus, you apply this process, and you're going to get contributions from Maslow index 0 disks. Okay. So I'll say a little bit more about what the form this transformation takes. Okay, so you can choose coordinates. Of course, I'm working in dimension 2, and my L0, that's one object in the family, is just a 2 torus. This H1 is just going to give you a unitary element squared. All right, so for example, I mean, of course, it can be something kind of complicated, but in a particular case where all the disks in this family lie in multiples of a particular class, beta, particular relative class, then the transformation you're going to get is going to act on these coordinates by this type of transformation. So it's just going to multiply each coordinate by a power series in this variable z beta. So z beta will be this thing here. So it's t to the area of beta times what I'm writing z to the boundary of beta. So the boundary of beta is, of course, a class in h lower 1 of the torus, and it gives you a function on h upper 1. All right, and this h I of z are power series, the rational coefficients, and leading terms to 1. All right, so that's the type of, so it's kind of,
Has it been important yet that you're working with tori?
yes. Otherwise, well, I mean, oh, you mean versus another type of smooth surface?
Yeah.
No, I don't suppose so. But of course, this is the case that I'm looking at sort of SYZ symmetry, so that's why I'm restricted. Right. Okay, so this is my quick summary of this reconstruction problem. Okay, so let's see. Well, of course, that sounds like very nice, but there's some kind of basic issue with this problem, with this method, which is that it's very difficult to calculate these Maslow index 0 disks. And that's not necessarily just a technical problem, but it's actually something kind of conceptual there, which is that it's not really, the count of these Maslow index 0 disks you're doing is not itself an invariant, right? So, I see.
Which means not at a fixed point in your path.
What do you mean? No, I mean just in the parametrized moduli space is itself can bifurcate as you deform the path. That's what I'm saying. So.
Well, but surely there's a fixed transformation from the start to the end.
Yes.
Change.
Yes, there's a fixed transformation from the start to the end, but the exact moduli spaces of disks that implement that.
Yes.
Yeah, that's right. That's the thing that's not invariant. Yeah, that's right. The transformation from the start to the end is canonical. That's right. Because if there's you're kind of homotoping one object to another, and then if you do a homotopy of homotopies, there's an equivalence between those transformations. That's correct. But actually, the moduli spaces of disks themselves are not stable. So, yeah. So basically, the point is you can have bifurcations in this family. So, for example, what you can have is if I took this family of tori, maybe I have some kind of contribution from this class beta 1, some kind of contribution from this class beta 2. And now if I maybe move this thing a little bit, then somehow these two disks could collide and become one big disk, one class beta 1 plus beta 2. Okay, so this is what I'm calling walls of the second kind. So it's not really those. It's actually a wall in the space of, well, it's a bifurcation in the space of Maslow. It's a bifurcation in the parametrized modular space. Okay. So I'm saying this is quite different. Okay, so basically what can happen in our case is that disk can bubble into other disks. In principle, you could also have a phenomenon where the disk actually just sort of could collapse to a point that actually that cannot occur. Okay.
On the beta 1 and beta 2 disks
Yeah.
is still there.
Yeah, they can also be still there. Yeah, yeah. But I mean, yeah. But there's. I'm trying to address it by birth here. Yeah. Okay, yeah, that's right. Okay. So I want to say. So I'm saying that it makes it difficult to count this. I wanted to point out to Yu Shen Lin, who, in at least some cases of particularly fiber K3 surfaces, has actually techniques to actually calculate the space of this on the node. But I'm not going to do anything that sophisticated. Okay, so this is kind of the basic issue that we want to circumvent somehow. Okay. So the basic idea is that what we want to do is actually just, somehow, it's not very canonical, these counts of Maslow's index series, but the idea is that we want to just look at a particular tori, and the only tori that I want to actually consider are ones that live very close to the boundary of this moment polytope. Well, it's not really a polytope because there's no globally defined moment map, but I want to consider tori very close to that tori's boundary, to the boundary divisor. Okay, so I'm just imagining here, so this black hexagon is sort of the boundary divisor. This red thing here is some half of tori, and I want to count these Maslow's index 0 disks that appear in this family.
Is your picture drawn correctly in the sense that the disks never hit the boundary divisor?
Yes. Yes. They live entirely in the complement. That has to do with the fact that they're Maslow's index 0, and the divisor is anti-canonical, so they intersect with the divisor that have higher Maslow's index. Okay. So now there's basically just an observation like you can make. So this problem is that if you take this path, dt, d of t, and you let it collapse onto the boundary divisor, then eventually in any particular homotopy class of disk, that moduli space is going to stabilize. So basically, at some point, as you move close enough to the boundary, you're not going to have any more bifurcations. Okay. So, right, so yeah, basically, as you move this path closer, you're not going to see this wall crossing of the second kind. And so this is kind of inspired by Gross-Hacking-Kiel. I'll say more in a minute what the Gross-Hacking-Kiel scattering diagram actually is. But one of the interesting things about their work is that they construct this scattering diagram as what I'll say is an asymptotic object. So there's perhaps many different things that could be called the scattering diagram associated to this log labial surface. The one particular one that they actually use kind of involves really exactly this process of sort of looking at things from a long way along, sort of zoomed out. Okay, so maybe I'll try to justify what's going on here. Basically, the idea, maybe this picture. Okay, so maybe I'll just, well, I should have actually both the text and the picture at the same time. The idea is what you're going to do is you're going to take this family of disks, this family of tori, and let it collapse onto the boundary and see what can those disks limit to. Okay. Basically, what they have to limit to are holomorphic spheres in the compactification that are tangent to the boundary divisor in a certain way. Now, okay, so, but that's something you can try to understand. All right, so let's see, we go back a little bit. So yeah, so as you collapse onto the boundary divisor, these holomorphic disks approach holomorphic spheres in Y. So one way to justify that is using sort of Gromov compactness theorem, for example, this target local Gromov compactness by Joel Fish. Now, that sort of tells you something. Okay, so you know that some of the disks are sort of converging to things like this that intersect the smooth part of D, but of course, you're typically going to have a lot of disks that sort of go into the node. There's many different disks that go into this node. But you want to understand what those things look like. So one trick you can use, which again is I'm going to exploit heavily, is to just sort of successfully blow up nodes. So this is what I call toric blow up, because the boundary is locally toric, so if you start blowing up nodes of the boundary divisor, that kind of looks locally like the toric picture of a blow up. Okay, so we're going to blow this thing up iteratively. And now what I'll see in this sort of picture is that as I collapse here, what I'm worried about is that somehow the moduli space associated to this class could have some kind of birth or death phenomenon where, disks in these classes come together. But in fact, looking in the limit, you can see that actually these disks, I'll say a little bit more, there's actually more that we know coming from Gross and Kiel about these moduli spaces of this, but you could use that to argue that as you collapse onto the boundary, actually this moduli space of this won't experience any wall crossing of the second kind, any kind of birth or death involved with these other disks. All right. Great. And this blowing up the divisor, I should say, is also one of the things that we really have to exploit in dimension 2. It's really an artifact of dimension 2.
So why does this really collapse to spheres? Because if the first reaches the edge,
Yeah.
the first collapses to a circle. Why can't the disk also, why does it have to contract to?
Yeah, they won't contract onto. Yeah, they won't contract that way. I mean, it will be the disk. The loop that it will bound is the disk. Is the loop that is collapsing. Yeah. All right.
So that's kind of topological.
Yeah. All right. So what this suggests now is that. Well, so what this picture suggests, is that what's actually happening. So what this picture is sort of suggesting is that, of course, that these disks here should be closely related to these curves, right? These closed curves in Y, in the pair YD. And that's actually going very much in the direction we want, because that's actually the curves that are used to define the GHK scattering diagram. Okay. So I'm going to review this. Okay, so this slide, okay, there's a lot of text here. This slide is basically what Gross and Kiel use as the definition of the scattering diagram. So what you do, so it's defined in terms of certain relative Gromov-Witten invariants, which I'll describe. So what you need to do is you start with your surface YD, and what you're going to do is you're going to iteratively blow up nodes of the divisor. So you form these toric blow-ups. Okay, now if C, so let's perform a toric blow-up. Okay, I'll sort of create many new components of the boundary divisor. Let's let C be a single component of this D tilde, and let's let D prime basically be the union of all the other irreducible components of the divisor D tilde. And let's take the complement of that. Okay, let's let Y tilde 0 be the complement of those other components. Okay. And, all right. So that's basically our target geometry. The curve classes we want to consider are classes of the form beta, where beta intersect this particular component is some integer, some positive integer, and beta intersected with every other component is 0. Now you can consider, in that situation, you can consider this relative, the moduli space of relative stable maps to Y tilde relative to C in this class beta. This is genus 0, with full tangency of order k beta at an unspecified point, that should say, of C. Okay, so that's a moduli space. Then you can do something that's a little bit unnatural at first sight, which is look at the subspace of those maps whose images lie in Y tilde 0. So just sort of ask that, just ask that these maps that don't hit are just disjoint from this D tilde prime. So that seems kind of a weird thing to do. But there's actually a very nice argument in this paper called The Tropical Vertex by Gross, Pandarapani, and Siebert, which is also reused in this GHK, which is that space is actually it's actually compact. Okay. So that's actually a very nice argument that you can look up there. So, yeah, what you're kind of worried about is that, you have these relative maps with tangent C on C. You're worried that that point of contact with C can kind of walk off to infinity. But actually, you can argue that that does not occur. In fact, okay, there's nothing that sequence could converge to in this moduli space. All right, and then we get a relative Gromov-Witten invariant n sub beta, which is the virtual count of these curves, and the Gross-Hagenkiel scattering diagram is defined precisely in terms of these data. Okay, so let's just draw it. Let's just draw a picture of it. So this was some kind of very simple picture of these relative Gromov-Witten invariants. Okay, so here's y tilde. This C is the component I'm interested in. And then, okay, I want to consider curves that are disjoint from the other components. And so then you draw, so given all these data, all these n betas, then you construct an affine manifold B, which is actually just the intersection complex of the boundary divisor. So that means it has a ray for each component of the boundary divisor and a cone for each node, and they're glued together in a very simple way. And but of course you get an affine structure by gluing together these cones, but it won't extend over the origin. So you basically just get an affine manifold with a very strange singularity at the origin. And then each rational ray in that affine manifold corresponds to a divisor in some toric blowup of y. And then for each of those, so each ray here corresponds to a divisor in a toric blowup. Then you do this construction of the relative Gromov-Witten invariance relative to that divisor. You get these n betas, and then the function associated with that particular ray will be this series here. Okay, and that is the definition. So I'm saying, so it's actually this k beta n beta times a monomial z to the boundary beta. I'm thinking of the boundary beta, that's the boundary loop that really is sort of collapsing when you go to C. And then that function will give you that plays the role of the wall crossing transformation in this Gross-Hagenkiel story. All right. Okay. Yeah, and so this very nice formula. Right, I'll just make the remark that if you make the ansatz that this n betas, of course this is kind of a well-known thing, but yeah, maybe I'll just recall it. Then if you make the ansatz that this n beta is equal to, let's see, if you were able to argue that that was true, then you would get exactly the standard sort of cluster transformation. As the output of that construction. All right. Okay, that's the Gross-Hagenkiel scattering diagram. All right, so at this point, I want to relate the discounts that I was doing before in the reconstruction problem to closed curves, the closed curves that are used in the construction of the Gross-Hagenkiel scattering diagram. So something technical has to happen at this point, right? Like it can't. Okay, so the technical
Does
thing I want
something
to do.
technical have to happen at this point if you assume all possible foundations of SFT?
Well, that's what I'm using. Yeah. So yeah, I mean, I'm using symplectic cutting and sum, so that's kind of an SFT type operation. Yeah, so that is what I need to use. Yeah, that is what I need to use. I regard that as somewhat technical. I mean, I'm going to do exactly that. So to understand the disk in this y0 tilde, what I'm going to do is perform a symplectic cut along a neighborhood of this divisor that I'm interested in. So I'm going to focus on one of these rays. I want to figure out why are the disks that are contributing to the wall crossing near this divisor controlled by the moduli spaces of closed curves in the Gross-Hagenkiel scattering diagram. So what I'm going to do, maybe I should actually show you the picture, is I'm going to perform a symplectic cut near that divisor. So I have my family of Lagrangian tori here, this red path, near this divisor C0 in some toric blowup, and I have this class beta, and what I'm going to do is I'm going to generate the target by sort of splitting off a piece of the normal bundle of C null. Okay. I'm going to relate then the count of these disks to the count of these configurations. Okay, so now I'm going to have this sphere here, tangent to C0, tangent to this thing, and also some disks inside with boundary on the Lagrangian, with Lagrangian boundary condition that are, again, tangent to that C0 from the other side. Okay, so maybe I'll say that in writing. That's basically the picture. So basically I'm writing my Y0 as a symplectic sum of Y0 with the projectilized normal bundle of C0. And I'm performing the cut in such a way that the Lagrangian boundary condition is staying in the part that's kind of being cut off. Okay. So then you are applying a symplectic sum formula, or a symplectic sum formula to relate the disks you want, the moduli spaces of disks with boundary on this family, to relative moduli spaces on one hand of these closed curves in Y0, and then disks in this thing. But of course, these disks are not terribly difficult to understand because this one is actually, a toric manifold now. And the closed curves you get really are precisely the ones that are used in the GHK scattering diagram.
Does the toric manifold contribute anything interesting at all?
This piece?
Yeah.
No, I don't think so. Yeah, I think this base is just, if you set it up right, you can just get through it. I mean, one thing to say is that the moduli space of the closed curves in Y0 was compact. Of course, I don't expect the moduli space of this and this thing to be compact, but I expect the evaluation into the divisor to be a proper map. So that's the compactness that I need to do this gluing.
So I'm vaguely aware that symplectic sum formula is sometimes controversial. Is this
Yeah.
one controversial, or is this one settled science?
I think this one is probably no less controversial than any of the other ones, but yeah, but this is what I'm advocating.
No, that's not true.
What?
A lot of the complexity appears in higher GS, right?
Okay.
So first of all, and then it depends on how many curves you have in C0. That's the whole complexity comes from there. In this case here, C0 is P1.
Right. Yeah.
So
Okay. So it's not. I mean, not as controversial as the general case. Yeah, I would like to say that, but I mean, this is what I'm, so that's why I said something technical has to happen. So yes. Okay. So I did, of course, want to cite the people who proved theorems like this. So Lee, Ruan, Einel, Parker, Jim Lee for the algebraic geometry case. That's kind of just symplectic sum formulas in general. I want to give some more specific references for arguments that are actually very close to this in spirit. So there's this work of Nishinu and Siebert where they tried to understand Witten invariance of toric manifolds via tropical geometry. And it was exactly by this sort of degenerations like this, of course, but much more complicated ones. So basically, and there's also a subsequent paper by Nishinu by himself that studies disks. And it kind of, if you tried to apply what he does here, it would actually do this, but actually something even more complicated. Because it involved degenerating the interior as well. I also wanted to cite some work by Mohammed Farajadeh Tehrani, who applied really a morally almost equivalent trick in the case of considering open Gromov-Witten theory of the real locus in a Calabi-Yau threefold. In certain cases where the real locus is a sphere or a projective space, he has an argument basically similar to this where you degenerate, you do a cut along a neighborhood of the Lagrangian and sort of cut that out, and then it relates the open Gromov-Witten theory with boundary on that Lagrangian to closed Gromov-Witten theory of a different manifold. Okay, so it's really morally very safe.
Can I ask my question again? So do you appeal to someone else's symplectic sum formula, or do you prove one yourself?
You need to prove one yourself, yeah.
So do you in fact prove this one, or like, will you prove this one in the future, or
Yeah, I don't have a proof of this in hand right now. Okay. But I think this is the way that this will go. Okay. All right, so, okay. So now, okay, that's very good. That's very good, but of course this kind of works one divisor at a time, so I'm kind of analyzing one ray at a time. All right, so, but now it becomes a problem, right? Because I can't just analyze one ray at a time. I have to analyze this whole scattering diagram. And, okay, but the problem is, okay, so what I'm doing is, this is like some form of space, saying you generate the complex structure in some way, and then you understand this moduli space. Okay, but now I need to understand this other moduli space, where I need to generate the complex structure in a different way. Okay, but can you really, okay, but when you change now how you're generating it, maybe this wall crossing of the second kind occurs. Maybe everything goes haywire. Okay. So, all right, so since the discounts are not entirely stable, it's important to understand whether the different degenerations are compatible. Okay, so basically what you now need to do is understand what happens when you consider several rays. Well, so that means you have to consider several divisor components, perform toric blow-ups, and then, so what I'm going to do there, the trick I'm going to do is do this toric blow-up thing again. I'm going to perform several toric blow-ups to make the divisors I'm interested in disjoint. And then, so that's another thing, again, I'm exploiting dimension 2. And so then you can really treat this thing as symplectic sum along a disconnected divisor, which is smooth. So so one thing I'm trying to do here is, only consider this symplectic sum for smooth divisors. In principle, of course, you could also do it for non-smooth divisors, but it involves more sophisticated Gromov-Witten theory, not relative Gromov-Witten theory, but log Gromov-Witten theory. Okay. All right, so this would be just a simple picture. I want to consider the disk contributing to these 3 rays. So these 3 rays correspond to 3 divisors in this toric blow-up, and I could generate along those 3 rays simultaneously. Okay. All right. So, but now, this tip, with that trick in hand, then you can do basically any collection of rays, any particular finite collection of rays simultaneously. But now, once you can do that, what you can argue is that, okay, actually, if you work order by order in the Novikov parameter, only finitely many of the rays contribute to any particular order. So, what you can do now is you can sort of do an inductive process where you work order by order to higher and higher orders, and you work with sort of more refined degenerations, okay, by more blow-ups, more and more refined degenerations. You can calculate this wall crossing transformations to any desired order, and, okay, you can match it to this Gross-Hackney-Kiel description. Okay, and that's the argument. So that means that, okay, so then the summary is that for families of Lagrange tori LBT sufficiently close to the boundary divisor, these wall crossing transformations are indeed given by the functions that you would expect from this Gross-Hackney-Kiel picture. All right, so this shows that the mirror, sort of the mirror, I'm trying to construct the mirror somehow, so I'm constructing the mirror at infinity. And so that is controlled by this Gross-Hackney-Kiel scattering factor.
Can I ask a question? So,
Sure.
I vaguely recall about this scattering diagram, there's some sort of ludicrous fact that if you know what the sort of total product is in any sector, then you know all the rays. Is that true?
Well, yeah, well, okay, so that's like, right, that's like this considered Soibelman lemma, so to speak.
Yeah.
Yeah, I think there's something like that.
So is that true for any sector?
Not entirely sure. Yeah.
Well, the nature of my question was, if that was true, wouldn't it be enough to just match a single array?
No.
Yeah. Okay, if that were true. Yeah.
But that's why I was asking if that was true or false.
Yeah.
Possibly correct that much.
Well, I mean, I don't think it could be enough, possibly be enough to match a single ray. I mean, because there are.
You'd have to know that
different
ray sat in
scattering
a
diagrams.
sector that was isolated in its sector.
Which
Yes,
it usually isn't.
Yeah.
So that's
What's that?
I see.
Yeah.
Which is wrong. I see. But otherwise, would that be true?
Not sure.
All right, so let's see, I'll finish up here with just a few remarks about what you can do if you have this in hand. Okay, so the point of the first part of the talk was just like, okay, how can we understand the scattering diagram? Can we get this to make sense in symplectic geometry? All right, so I'm claiming that you can via those arguments. All right, so what can you apply this to? Well, so the point is we kind of understand the mirror at infinity. So I'm kind of here now, sort of following Gross-Hackney-Kiel again. So you can try to, once you understand the mirror at infinity, you can try to understand other pieces of the symplectic geometry that kind of live at infinity. All right. So this, okay, so we have symplectic homology. I guess I'm kind of just reviewing here. This is kind of a quick review. So it's a symplectic homology for Liouville manifolds, okay, such as my U. This is complement. The way it's defined, of course, is by completing U to U hat by attaching a positive half of symplectization along a contact type hypersurface, and then you take the Floer homology of a Hamiltonian which grows on the end. And of course, this thing captures the symplectic homology, captures the classical topology of U and the closed ray orbits in sigma in a deformation invariant way. So here's just a simple picture. Okay, so here's my picture of U. Okay, maybe this slide is too embarrassing. Picture. Okay. It's too embarrassing. Okay, let's just skip that.
Let's see that slide.
Okay, let's just not do it. Okay, so one nice thing you can do in understanding this geometry is you can understand what the basis of the symplectic homology is. All right, so in this case, so in the Slot-Labial surface case, sigma, this contact type hypersurface, well, it's actually kind of like this path of Lagrangian tori near the boundary divisor. So sigma will be a 2 torus bundle over the circle with non-trivial monodromy. Now, you can arrange things, basically using this sort of locally toric picture near the boundary, you can arrange things so that the ray flow is actually tangent to the torus fibers, and it translates each one by a certain vector VT and R2. Okay, so you can arrange that the vector, another thing you can do is you can arrange that this vector rotates monotonically as we vary the fiber. Okay, when this when this vector has rational slope, then that's when you get periodic orbits. So the point is the symplectic homology is trying to capture periodic orbits in this contact type hypersurface. And let's see. Yeah, so when do you get periodic orbits? Well, you're translating this torus, and you get periodic orbits when that translation closes up. Okay. And using this sort of picture, you can, the theorem that you can calculate the degree zero symplectic homology of U. And in fact, if you look at what exactly you get here, you actually get a basis indexed precisely by the integral points of the affine manifold that where the scattering diagram appears. Okay, so there you have it. So this is a picture of this ray flow. So the point is you're translating each torus. So basically the torus is here drawn as a square with sides identified. And the translation is sort of along these blue lines are the integral curves of the characteristic foliation. So okay, so here they're closed. Here maybe that's the irrational slope. So there's no closed leaves, and maybe that's another rational slope. And then here I've sort of drawn a picture of the affine manifold with this basis listed. So what can we do with this? Okay, so how is this related to what we did before, right? So it's related to what we did before because this degree zero symplectic homology can be interpreted as functions on the mirror. Okay, functions on the moduli space of objects. So that's basically via this what's called the closed open map. Okay, so what this involves is, so you have some torus, so it's somehow I want to produce, I have each torus, I have a chart there, right, this H1 of L U lambda, and I want to produce a function on that, okay, from a symplectic homology element. And what I do is I count cylinders that are, well, they're sort of half cylinders, they have boundary on the Lagrangian, and they're asymptotic to a symplectic homology orbit. And you have to, of course, in this case, these things aren't exact, so you have to weight them by the area and the holonomy of the local system. All right, so what good is that? Well, okay, so let's take one of these points in this affine manifold. So remember those points, well, they correspond actually, well, so for each point, in each integral point, of course, you have a ray through that point. And of course, that ray corresponds to a divisor component in some toric blowup. And so if you look in that model, you have a small torus that links that divisor, and also you have a generator. Okay, that's coming from the previous theorem. You have a generator that links that divisor. And for this particular situation, you can argue that in that particular chart, okay, so that this particular element, theta p, I'm here following the Gross-Hector field notation, that particular element maps to a monomial in this particular chart. Okay, and of course, there's a C, there's possibly some wall crossing along C, but actually the monomial you're getting is the one which is invariant with respect to those wall crossings. So it does make sense. Okay, so that's useful. So from that point on, right, we're actually, basically at this point, maybe we should just say I'm basically just following Gross-Hagen-Keil, like almost word for word. So the point was, this is sort of my picture here. Okay, this was my open closed map, closed open map. So here's the symplectic cohomology orbit, and I have half cylinders that have boundary on the Lagrangian. Okay, but of course I could move that Lagrangian somewhere else, and consider the cylinders, the boundary on that other Lagrangian. Okay, and that corresponds to really trying to evaluate this symplectic cohomology element as a function in other charts. Okay, so now here, again, I have to sort of appeal to some sort of general invariance property, which says that, there's a compatibility between these closed open maps and actually the wall crossing transformation, actually the gluing maps in the moduli space of objects. So that actually so basically it's the invariance property, it's kind of like in FOQ, the invariance of the potential function. It says that actually this closed open map actually defines an analytic function on this moduli space of objects. But of course then, if you understand the wall crossing, then you can actually figure out, what this function looks like in all the other charts, right? Because it's a monomial in this one chart, but then you move to another chart, you apply this wall crossing transformation, this monomial becomes some Laurent polynomial, you keep going, it gets bigger and bigger and bigger, and that is exactly this process which is axiomatized by Gross-Hagen-Keil in the notion of broken lines. Okay, so basically, that's exactly how they're defined. So that there's really not much to say to match those. And of course, once you have this guy. And then you can also understand the ring structure. So this picture here. So you can visualize evaluating these things. This is a very beautiful thing from Gross-Hagen-Keil. You can visualize evaluating these things by looking at, you have a torus here, which is kind of in some sector, and then the symplectic cohomology element you're looking at corresponds to an asymptotic direction. And you look at these rays that end here. And of course, you could be in some other sector, so then what happens is when you cross one of these lines, you apply the wall crossing transformation. There's several possibilities for how you can continue. And choosing one possibility gives you a broken line ending at this point. And then to figure out what's the product, so if I want to figure out, so remember these theta functions are indexed by integral points to this affine manifold. Well, what's the coefficient of theta r and theta p times theta q? Well, you do exactly what Gross-Hagen-Keil tells you. You look at this, you look at the torus, you look at this chart, kind of corresponding to the point r in the affine manifold. So it's something in this sector, and then you take theta p and theta q, you evaluate them in here, take their product, and then look at the coefficient of the corresponding monomial. And you know that theta r is a monomial in that chart, and that's how you can evaluate this. Okay. So I'll just wrap up here. Okay, so the construction, so I'll just sort of summarize what we did. So the construction of the mirror is governed by these massive index zero disks. These counts of these disks are not particularly stable, but they do kind of stabilize if you think about what's happening at infinity as before I go through the boundary divisor. And the asymptotic disk counts are related to relative Gromov-Witten invariance via a symplectic sum formula, and that's how you relate, you can relate directly to the moduli spaces that are used in the Gross-Hagen-Keil scattering diagram. And basically that tells you enough to construct the mirror at infinity, and then once you know the mirror at infinity, you can try to study other structures that make sense there. So, all right, that's the end. Thank you.
Are there any questions for the speaker?
So
Hi.
your construction does something about the polar you're looking at the boundary
Yes.
and devices.
Yes.
Is there any kind of way to extend to something away from the divider?
Well, yeah, you can, because you can try to sort of, one thing you can do is try to well, these things are legal manifolds, so you can kind of try to flow in. That's something you can try to do. You can try to extend these torus vibration in. Of course, eventually there's critical points of that flow. So you'll kind of, I mean, of course, the pores as you flow it will then form singularities, and you'll get some singular tori. But yeah, I mean, I think basically, if you look at this, you can pretty much construct. I mean, yeah, another thing you can do is think about, trying to, define the mirror as to be as large as possible by sort of extending it to the maximal domain of convergence of the wall crossing transformation. And I think that it seems to, well, I don't know.
I
I'm
mean,
not
for
exactly sure. I
example,
think you
you
get
consider
pretty
the
much
case
everything
of
except the
toric
singular
manifold,
powers. Yeah.
and then the neighborhood of toric divisor is this picture,
Mm-hmm.
and then but somehow all the way of merging for those tori is just trivial.
True,
So
true.
it
Yeah,
doesn't
true.
seem that just like an interior, so.
Yeah. You don't get the most interesting tori objects this way. That's right.
Can you clarify where exactly you use dimension 2?
Well, I used it for, a bunch of tricks, mostly involving the combinatorics of the boundary divisor. Basically, the fact that it's a cycle of curves and that you can sort of blow up. I mean, basically, this process of iteratively blowing it up. I mean, for example, you can always.
So what do you actually need that for?
To be able to work relative to smooth divisors. I mean, so if you're willing to work, but, I think there is a higher dimensional generalization where you just drop this assumption entirely and work with log Rome of Witten theory.
Yeah.
In which case, then you have to work relative to normal crossing divisors.
But that's the only place you use it.
Yeah.
Okay. Maybe ask one more.
There is another place,
Okay.
which is that I only ever had to consider. I wanted to consider all the tori near the boundary divisor, and they were all smooth. That's another place. In higher dimensions, typically you're going to get singular fibers all the way out to the boundary divisor. Yeah.
I think in the case of higher dimensions, you
Yeah.
may have a higher mass index -2 or -1.
Oh, that's true, of course, too. Yeah, that's true, of course, too. Yeah, the dimensions to the mass limit zero disks are different. Yeah.
All right, if there are no more questions, let's thank James again.